Over the past century, humanity has constructed a remarkably precise understanding of our world, known as the Standard Model. This achievement represents a pinnacle of human knowledge, clarifying the mechanisms behind atomic bonding, stellar combustion, and gravitational forces keeping us grounded. As the most rigorously tested and validated theory throughout human existence, it paints a picture of a cosmos that operates uniformly, follows predictable patterns, and provides a stable environment. Yet there exists a fundamental issue. Reality itself refuses to cooperate. When we direct our astronomical instruments skyward, we encounter phenomena that resist explanation within our framework. Structures emerge that exceed theoretical size limitations. Material velocities surpass calculated expectations. Energy manifests from apparent nothingness. The situation resembles discovering an unexpected chamber in a dwelling you personally constructed. Its presence defies logic, yet undeniably exists. These aren't minor mathematical discrepancies. They represent glaring inconsistencies, indicating our grasp of existence might contain fundamental flaws. We're encountering objects that contradict Big Bang chronology. Signals originate from supposedly vacant regions. Constants we measure demonstrate potential variability. Our examination today encompasses all available data. From enigmatic cold regions in deep space to absent matter in our cosmic neighborhood, we'll explore 50 instances where the cosmos defies our predictions. The current state of affairs suggests comprehensive understanding has become elusive. Progressive investigation reveals increasing strangeness. Our examination begins with cosmic cartography. Observing the universe's most ancient illumination, the cosmic microwave background radiation, should reveal uniformity resembling television static, displaying minute temperature variations distributed evenly throughout the celestial sphere. This expectation stems from the cosmological principle, suggesting spatial homogeneity, regardless of observational direction, lacking privileged locations or irregular configurations. However, observations revealed the cold spot anomaly. Initially identified by the WMAP satellite and subsequently verified by the Planck satellite, this represents an extensive southern hemisphere region exhibiting troubling characteristics. Its temperature registers significantly below surrounding areas, approximately 70 to 150 microkelvin cooler. While this differential might appear negligible, cosmological standards classify this as distinguishing minor fluctuations from catastrophic deviations. Statistical probability suggests such a formation shouldn't exist. Standard model calculations indicate odds below 1% for a spot exhibiting these dimensions and temperature appearing randomly. It manifests like a dark blemish on an otherwise unblemished surface. Scientists pursued their standard protocol, investigating potential errors. Instrument calibration underwent scrutiny. Dust interference possibilities received examination. Comprehensive checks were performed. The anomaly persisted. Its reality and magnitude remain undeniable. If the cold spot represents genuine phenomena rather than error, what explains its existence? The most reassuring interpretation involves a supervoid. Envision an immense spatial region spanning roughly 1.8 billion light-years, situated within the constellation Eridanus, exhibiting significantly reduced galaxy, star, and gas cloud concentrations compared to typical regions. Essentially barren, isolated expanse. The theoretical framework appears straightforward. As cosmic background radiation traverses toward our observation point, it passes through this vacant region. Diminished gravitational influence results in energy loss as photons emerge from the far side. This mechanism, termed the integrated Sachs-Wolf effect, correlates reduced energy with decreased temperature measurements. Problem resolved, seemingly. Reality proves more complex. Surveys confirmed a void exists in that direction, the Eridanus supervoid, representing the largest mapped void discovered. However, a critical discrepancy emerges. The void's emptiness proves insufficient. Even this colossal vacancy explains merely 10 to 20% of observed temperature reduction. Mathematical calculations fail alignment. The void exists certainly, yet resembles attempting to explain shattered glass with a small stone. Damage magnitude exceeds causal capacity. The question persists regarding the remaining temperature deficit's origin. This consideration introduces an unsettling theoretical proposition that generates legitimate scientific apprehension due to its science fiction resemblance. What if the cold spot originated beyond our universe? Theoretical physicists, including Laura Mersini-Houghton, propose our universe might not represent solitary existence within cosmic foam. A multiverse framework could encompass our reality. During our history's violent expansion throughout the Big Bang, our cosmic bubble potentially contacted a neighboring universe. Two-universe collision would generate observable evidence, a distinctive mark. Impact forces would displace matter, creating regions exhibiting unique properties, potentially manifesting as cold spots. Clarification necessary: this perspective lacks mainstream acceptance, representing radical speculation. However, the mere consideration of this hypothesis indicates the anomaly's profound strangeness. We're examining a celestial region refusing conformity with understood reality, compelling consideration whether perhaps our reality possesses boundaries and external forces impacted them. Orchestrated textual reformulation, preserving analytical depth and argumentative progression. Continuando a reescrita. Preciso manter o mesmo nível de detalhe e progressão de ideias, apenas usando palavras diferentes. If universal collision evidence seems insufficiently peculiar, consider the axis of evil designation. This term, contrary to political connotations, represents actual cosmological nomenclature, recalling previous statements about universal randomness and spatial directional absence. Scientific analysis of cosmic microwave background, temperature fluctuations, revealed pattern formation, distinct alignment characteristics. Hot and cold regions don't distribute randomly. They demonstrate alignment along specific axes. The most unsettling aspect involves this axis's near-perfect correspondence with our solar system's plane. Consider this realization's absurdity. Discussion concerns background radiation originating 13 billion years previously. Earth bears no relevance. Solar characteristics prove irrelevant. Planetary orientation shouldn't matter. Yet data suggests universal orientation around our location. Copernicus devoted his existence proving we don't occupy the universe's center. The axis of evil hints we might possess special significance after all. More plausibly, systematic errors plague our cosmic understanding. Perhaps strange topology exists, like donut-shaped universal geometry forcing these alignments. Regardless, the map lacks randomness. Directionality exists without explanation. Continuing with cartographic anomalies, let's examine cosmic traffic patterns. Within expanding universes, everything should recede from everything else, resembling dots on an inflating balloon. Observing sufficiently distant regions, expansion should dominate as the primary force. However, 2008 brought discoveries from Alexander Kashlinsky's team, revealing alternative patterns. Examining hundreds of galaxy cluster movements revealed they weren't merely expanding. Drift patterns emerged. A massive galactic river spanning billions of light years flows uniformly in one direction at nearly 2 million miles per hour. This phenomenon received the designation dark flow. It operates independently from cosmic expansion, resembling corks tossed into an exploding lake drifting sideways against prevailing currents. The drift heads toward celestial regions between Centaurus and Hydra constellations. Whatever exerts this pull must possess enormous scale, exceeding anything observable within our universe. Yet invisibility persists. Flow simply proceeds toward that destination. Partial motion derives from a local phenomenon designated the Great Attractor. This gravitational anomaly resides approximately 250 million light-years distant, precisely within the zone of avoidance, the sky region obscured by our Milky Way galaxy's dense dust. Direct optical telescope observation remains impossible. It conceals itself behind cosmic curtains, yet its influence proves detectable. Our galaxy and surrounding systems experience attraction toward it at 600 kilometers per second. X-ray surveys revealed massive galactic clusters in that region, including the Norma cluster. However, a significant discrepancy exists. Calculating all visible mass within the Great Attractor reveals insufficiency. It accounts for perhaps half the gravitational pull. The remainder remains missing. We're experiencing attraction toward a dust wall by gravity sources we cannot fully account for, resembling feeling a fishing line tug while observing only shadows beneath water's surface. The situation expands. Beyond the Great Attractor, we discovered it merely represented a pebble. The boulder lies behind it, the Shapley supercluster. This represents the most massive nearby galactic concentration, approximately 650 million light-years distant. It contains over 8,000 galaxies with mass totaling 10 million billion suns. We're falling towards Shapley, yet even Shapley demonstrates motion. We recognize our Milky Way, the Great Attractor, and Virgo Cluster all constitute suburbs of a titanic structure called Laniakea, a galactic supercluster resembling flowing light tendrils. Laniakea translates as immeasurable heaven in Hawaiian, fitting appropriately. We represent tiny specks sliding down one of its gravitational valleys. Yet even Laniakea moves. Dark flow suggests something beyond these superstructures. Something outside our observable map's edge tugs the entire web. We're small fish in an exceptionally vast current. Let's discuss size limitations. Cosmologists maintain a rule termed the end of greatness, basically stating universal structures cannot achieve excessive dimensions. Once observation extends past approximately 1.2 billion light-years, everything should appear smooth and homogeneous. Gravity simply shouldn't construct larger things. Insufficient time has elapsed since the Big Bang. However, apparently gravity missed that memo. 2021 brought astronomers' discovery of the Giant Arc, a crescent-shaped galactic arrangement stretching a staggering 3.3 billion light-years across, covering substantial observable sky portions. This thing exceeds theoretical limits threefold, resembling discovering a human bone 30 feet long. Biology claims it shouldn't exist. Physics claims the Giant Arc shouldn't exist. Yet there it persists, shimmering in Sloan digital sky survey data. Its existence challenges the cosmological principle itself. If structures this large can form, then our universal uniformity assumption proves incorrect. The map isn't just blurry, it might be fundamentally broken. Sometimes oddity concerns shape rather than size. Galaxies typically manifest in two varieties: spirals like ours, or elliptical blobs. They're messy organic shapes born from gravity and collisions. Then there's Hoag's object. It resembles something a science fiction artist drew. It's a perfect symmetrical ring of blue stars surrounding a disconnected yellow star sphere at the center. No spokes exist, no bridges connecting them, just a ring and core floating in perfect isolation. How does formation occur? Leading ring galaxy theory requires collision, one galaxy punching through another's center. But collisions leave mess, debris, tidal tails. Hoag's object is clean, pristine. No sign exists of the bullet galaxy that supposedly punched through it. It sits there 600 million light-years away, looking completely artificial. We have simulations for galaxy formation, and Hoag's object barely fits any of them. It's either a beautiful 1 in a billion natural freak, or a sign that galaxy-building methods exist that we haven't figured out yet. But Hoag's object is just a single anomaly. The problem worsens when strange behavior spreads across the entire sky. This is what we see with quasars. These are the bright hearts of distant galaxies powered by supermassive black holes blasting energy jets into space. Since galaxies are separated by billions of light years, their orientation should be random. A black hole in one universe corner shouldn't care which way a black hole in another corner points. They've never met, never communicated. Gravity proves too weak to link them over such distances. But in 2014, a study using the Very Large Telescope found that quasars across distances of billions of light years are aligned. Their rotation axes run parallel to each other. This is spooky action at a distance on galactic scale, suggesting these galaxies connect through some invisible framework. Maybe giant dark matter filaments we can't see. Or maybe they all experienced influence from the same Big Bang conditions, retaining a memory of a time when everything was touching. It forces us to accept a difficult truth. The universe isn't a collection of isolated islands. It's a web, and the threads connecting it are invisible to us. We're looking at a puppet show, but we can't see the strings. And if we can't see the strings, do we really know who or what is pulling them? Let's talk about history, specifically everything's history. Before launching the James Webb Space Telescope on Christmas Day 2021, we had a pretty confident story about how the early universe grew up. The standard cosmological model known as Lambda CDM gave us a clear, comfortable timeline. It said that after the Big Bang, the universe went through a dark age, a sea of neutral hydrogen gas, completely dark with no stars to light it up. Then, gravity began its slow, tedious work. pulling tiny gas pockets together into messy, chaotic clumps. These were the first baby galaxies, supposed to be small, weak, and irregular. Nothing like the beautiful spirals we see today. Over billions of years, these clumps would collide, merge, and gradually build up structure in a process called hierarchical clustering. Small things becoming big things over a long time. That was the dogma, written in every textbook, fitting the simulations running on supercomputers. But then James Webb opened its golden hexagonal eye, and within weeks, that story was on life support. The telescope looked deeper into the infrared than Hubble ever could, allowing it to peer back through cosmic dust to a time when the universe was only 300 to 500 million years old, redshift 10 and above. According to our models, this era should have been populated by those tiny, messy blobs. We expected to see the cosmic equivalent of toddlers playing with blocks. Instead, we found monsters. We found galaxies that were massive, bright, structured. They weren't messy blobs. Some had fully formed disks and even spiral arms. They looked like adults sitting in a nursery. One galaxy, GNZ11, appeared to be more massive than should be possible for its age. It was shocking because there simply hadn't been enough time for gravity to do its job. In the standard model, gathering that much gas takes time. Cooling it down so it can collapse into stars takes time. Spinning it up into a disk takes time. It's like planting an acorn and coming back an hour later to find a 100-foot oak tree with deep roots and full branches. Biology says that's impossible. Physics says these galaxies are impossible. And yet, there they are staring at us from the dawn of time, mocking our timeline. The data is so robust that some astronomers initially thought the telescope calibration was wrong. They couldn't believe their eyes. But as calibration was checked and rechecked, reality sank in. The early universe wasn't a slow waking up. It was an explosion of structure that we simply cannot explain. To understand just how bad this problem is, you have to look at the cold, hard numbers. In February 2023, a team led by astronomer Ivo Labbé from Swinburne University of Technology published a paper in Nature that shook the astrophysics community to its core. They identified 6 candidate galaxies from roughly 500 to 700 million years after the Big Bang. These weren't just big, they were impossibly heavy. The team calculated their stellar mass, basically how much star stuff they contained, by analyzing the light they emitted. The brighter and redder the galaxy, the more stars it has. The results were staggering. Some of these objects had masses as high as 10 billion to 100 billion times the Sun's mass. One candidate appeared to have a stellar mass comparable to our modern Milky Way. But remember, the Milky Way took 13 billion years of eating other galaxies to get this fat. These things did it in less than 5% of that time. Here is where the math breaks down completely. If you take the standard model of cosmology, you can calculate the baryon budget of the early universe. Baryons are just normal matter, protons and neutrons. We know how much normal matter existed back then compared to dark matter. It's a fixed ratio. You can't turn more gas into stars than you actually have available in a given region. But these galaxies are so massive that if the measurements are correct, they would have had to convert nearly 100% of the available gas in their dark matter halos into stars, and they would have had to do it with perfect efficiency. Real galaxies don't do that. Star formation is a messy, violent, and incredibly inefficient process. When stars form, they blast out radiation and supernova winds that push the remaining gas away, stopping future star formation. This is called feedback. Usually, a galaxy only manages to turn about 10 to 20% of its gas into stars before feedback shuts it down. For Labbé's galaxies to exist, they would have to be eating faster than the laws of physics allow. They're defying the cosmic limit. Essentially, they're heavier than the universe should have been able to support at that time. It's a paradox. Either our measurements of their mass are wrong, maybe the light is being contaminated by something else, like a black hole, or our understanding of how galaxies assemble is fundamentally flawed. If it's the latter, then the standard model isn't just missing a piece, it's wrong about the very beginning. If the galaxies are eating too fast, then what's lurking at their centers is even worse. We're talking about supermassive black holes. In the modern universe, these giants sit at the hearts of most galaxies, including ours. Sagittarius A star, The black hole in the middle of the Milky Way is about 4 million times the Sun's mass. They grow over billions of years by swallowing gas and merging with other black holes. It's a slow, gluttonous process, but we're finding them in the early universe too, and they're way too big. Take the quasar J0313, 1806, discovered in 2021. We see it as it existed just 670 million years after the Big Bang. At its core is a supermassive black hole weighing 1.6 billion times the Sun's mass. Think about that number, 1.6 billion. There's a strict speed limit for how fast a black hole can feed, called the Eddington limit. Here's how it works. As gas falls into a black hole, it heats up due to friction and glows incredibly bright. This light exerts pressure, radiation pressure, pushing outward against the infalling gas. If a black hole tries to eat too fast, the light it creates pushes the food away, choking off the meal. It's like trying to drink from a fire hose. The pressure pushes you back. Based on this limit, a black hole starting from a standard stellar seed, say the remnant of a massive star weighing 10 or 20 times the Sun's mass, would take almost a billion years of non-stop maximum speed eating to grow to the size we see in J0313. But the universe wasn't even a billion years old yet. The math simply does not allow it. Even if the black hole ate at the Eddington limit every single second of its life, which is unrealistic because food runs out, it still wouldn't be big enough. So how did it get so big? It's mathematically impossible to get there from a single star in the time available. This means one of two things. Either the Eddington limit can be broken, which would require some exotic unknown physics like super Eddington accretion, where magnetic fields somehow trap the gas, or these black holes didn't start as stars. They started as something else. Something massive, something that skipped the baby phase entirely. And that possibility scares physicists because it implies a violent mechanism in the early universe we've never seen. This brings us to one of the most terrifying and fascinating theories in cosmology: direct collapse black holes. This is the leading attempt to fix the timeline, but it requires conditions so extreme they sound like fiction. Usually, to make a black hole, you need a star. A massive star lives its life, burns through its hydrogen fuel, fuses heavier elements, and eventually runs out of energy. Gravity wins, the core collapses, and you get a black hole. But this process is limited by the star's size. The direct collapse theory suggests that in the strange, hot, dense environment of the early universe, you could skip the star part entirely. Imagine a gigantic cloud of pristine gas, hydrogen and helium floating in the dark. This cloud is millions of times the Sun's mass. Normally, this cloud would cool down, fragment, and break into thousands of smaller pieces, forming a cluster of regular stars. That's how physics usually works. Cooling leads to fragmentation. But what if the gas couldn't cool down? What if it stayed hot? This could happen if the cloud was being blasted by intense ultraviolet radiation from a nearby galaxy. This radiation would destroy the molecules needed for cooling, keeping the gas hot. If the gas stays hot, it doesn't fragment. Instead, gravity pulls the entire massive cloud inward as a single unit. Without the heat of nuclear fusion to push back, the cloud would just keep crushing down, getting smaller and denser until, snap, it punches a hole in space-time. Instead of a black hole 10 times the Sun's mass, you would instantly get one that is 10,000 or even 100,000 times the Sun's mass. A heavy seed. From there, it has a massive head start. It can merge and eat its way to 1 billion solar masses in record time, explaining the monsters we see with James Webb. It sounds like a neat solution, but it creates new problems. The conditions required for direct collapse, pristine gas plus a nearby bright galaxy to sterilize it, are incredibly rare. Simulations show it shouldn't happen often enough to explain all the giant black holes we see. And yet, because we see these monsters, something like this must have happened. The universe found a cheat code. It built giants before it built stars. And if that's true, then the early cosmos wasn't a quiet nursery. It was a factory of monsters collapsing entire clouds of potential stars into darkness in a single stroke. While we're questioning the timeline of giants, let's look at something smaller, but equally baffling: dust. Cosmic dust might sound boring. It's just soot basically made of silicon, carbon, and aluminum. But it's the key to understanding the age of things. It's the cosmic clock. Here's why the Big Bang didn't make dust. It only made hydrogen, helium, and a tiny pinch of lithium. Heavy elements, which astronomers call metals, are forged exclusively inside the bellies of dying stars. A star has to be born, live out its life for millions or billions of years, fuse atoms in its core, and then explode as a supernova to scatter that dust into space. Then that dust has to cool, clump together, and grow. It's a multi-generational process. You need grandmothers and great-grandmothers of stars to live and die to create enough dust to be visible. So when we look at a galaxy like A20744 YD4, located 13.2 billion light-years away, meaning we're seeing it just 600 million years after the Big Bang, we expect it to be clean. It should be a primitive object made of pure gas, but it isn't. When the Olma telescope, the Atacama Large Millimeter Array in Chile, looked at it, it picked up the thermal glow of huge amounts of dust. We're talking about 6 million solar masses of dust. This is a crime scene where the body is found before the murder weapon was even manufactured. How can a galaxy so young be so polluted? Even if the first stars were massive and burned out quickly, so-called population 3 stars, it's hard to explain how they produce this much material so fast. Some models suggest that supernova actually destroy dust as fast as they make it, blasting the grains apart with shock waves. So the dust shouldn't survive the very explosions that create it. So where did it come from? Some theorists suggest that maybe quasars contribute to dust formation, or the dust grains grow in the interstellar medium much faster than we think. But neither explanation fully fits the data. The existence of this dusty galaxy implies that the early universe was chemically mature long before it had any right to be. It suggests that star formation started earlier or proceeded faster than our models allow. We're looking at a teenager that already has wrinkles and gray hair. It just doesn't fit the birth certificate. If finding dust in a baby universe is confusing, let's try something even harder to swallow. Imagine meeting someone who claims to be older than their own mother. It sounds ridiculous, right? Biology doesn't work that way. Cause must come before effect. Parents must come before children. But in astronomy, we have a star that claims exactly that. Its catalog name is HD 15283, but everyone calls it the Methuselah star. It's a subgiant star located just 200 light-years away from Earth in the constellation Libra. It's moving incredibly fast through our galaxy, suggesting it isn't a local. It was likely born in a dwarf galaxy that the Milky Way ate a long time ago. But its speed isn't the problem. Its age is. Astronomers have been studying this star for over a century. By analyzing its composition, specifically how little iron it has, we can estimate when it formed. The less iron, the older the star, because early stars formed before the universe was polluted with heavy metals. The Methuselah star has almost no iron. It's practically pure hydrogen and helium. When scientists crunched the numbers in 2013, using the Hubble Space Telescope, they got an age of 14.5 billion years. Now pause for a second. The universe, according to our best measurements from the Planck satellite, is 13.8 billion years old. So, how can a star be older than the universe itself? It's the ultimate paradox, like finding a Roman coin dated 500 BC inside a dinosaur fossil. It shouldn't happen. Scientists have scrambled to fix this. They refined the models, looked at oxygen levels, and adjusted the error bars. They managed to pull the star's age down to about 14.3 billion years, with an uncertainty of 800 million years. If you push the math to the absolute limit, taking the youngest possible age for the star and the oldest possible age for the universe, they just barely overlap. But it's uncomfortable. It's a statistical squeeze. The fact that we have a star sitting right on the edge of the impossible suggests that either our understanding of stellar evolution is slightly off, or the universe is older than we think. Speaking of ingredients that don't add up, let's talk about lithium. If you baked a cake and the recipe called for 3 cups of sugar, but you only tasted 1, you would know something went wrong in the kitchen. Cosmologists have a very precise recipe for the Big Bang, called Big Bang nucleosynthesis. It calculates exactly how much hydrogen, helium, and lithium should have been cooked up in the first few minutes of the universe. The predictions for hydrogen and helium are spot on. They match what we see in the oldest gas clouds almost perfectly. It's one of the greatest triumphs of modern physics. But then there's lithium-7. According to the theory, we should see a specific amount of lithium in the oldest stars. But when astronomers measure it by looking at the Spite Plateau, a baseline of lithium in ancient stars, they find only about 1/3 of what the model predicts. Where did the rest go? Did the universe eat it? This is known as the cosmological lithium problem. And it's not a small error. It's a discrepancy of 300 to 400%. We've tried to explain it. Maybe our telescopes are missing that lithium. Unlikely. The spectral lines are clear. Maybe the stars destroy lithium in their cores. We modeled that. And while stars do burn lithium, they don't burn enough to explain this huge gap. Some physicists have suggested that maybe we need new physics. Perhaps unknown particles, like axions or decaying dark matter, interfered with the nuclear reactions in the first few minutes of time, destroying the lithium before it could settle. If that's true, then the lithium problem isn't just a missing ingredient. It's a fossil record of a ghost particle we haven't discovered yet. But for now, the recipe for the universe is missing a key component, and we have no idea who stole it. If missing atoms aren't big enough for you, how about missing galaxies? Our standard model of cosmology relies heavily on cold, dark matter. This invisible stuff provides the gravity that holds galaxies together. We run massive computer simulations, like the Millennium simulation, to see how dark matter behaves over billions of years. These simulations predict that every large galaxy like our Milky Way should be surrounded by a swarm of smaller clumps of dark matter. Hundreds, maybe thousands of them. These clumps should attract gas and form tiny satellite galaxies. The model says the Milky Way should be buzzing with them like bees around a hive. So, astronomers went out to count them, and they found about 50. Wait, the computer says thousands. The sky says 50. Where are the rest? This is the missing satellites problem. It's a massive embarrassment for the dark matter theory. Now you might ask, could they be there but just invisible? Maybe they're dark galaxies, clumps of dark matter that failed to catch enough gas to make stars. If that's true, then our galaxy is surrounded by thousands of invisible ghosts right now. Silent, dark halos passing through us without lighting up. Or maybe our theory of dark matter is wrong. Maybe dark matter isn't cold, slow-moving, but warm. Warm dark matter moves faster, which would smooth out the small clumps and prevent these tiny satellites from forming in the first place. That would fix the count. But changing dark matter from cold to warm messes up other things, like the structure of the cosmic web. It's a trade-off. We're stuck between seeing too few galaxies and breaking the physics that explains the big ones. So, is the Milky Way lonely, or is it haunted by invisible neighbors? There's another chapter in the universe's history book that seems to have some pages torn out. It's called the Epoch of Reionization. Here's the setup. After the Big Bang, the universe cooled down and filled with neutral hydrogen gas. It was a fog, an opaque, dark fog that blocked light. For hundreds of millions of years, the universe was effectively dark. Then something happened. The first stars and quasars turned on. Their ultraviolet light blasted the hydrogen atoms, stripping away their electrons, ionizing them. This cleared the fog and made the universe transparent, allowing us to see distant galaxies today. We know this happened. We can see the before, the cosmic background, and the after, the clear sky. But we can't get the timeline to work. When we look at distant quasars, we see something called the Gunn-Peterson trough, a signature that tells us when the fog cleared. It suggests reionization ended around 1 billion years after the Big Bang. But when we count up all the galaxies and quasars that existed back then, they don't produce enough light. It's a simple energy budget problem. To clear the fog, you need X amount of UV photons. The galaxies we see only produce Y, and Y is much smaller than X. So, what cleared the fog? Was there a population of massive, short-lived stars that vanished without a trace? Did black holes vomit out more radiation than we think possible? Or was there some exotic source of energy like decaying dark matter particles that helped burn away the darkness? We're looking at a clear sky, but we can't find the light switch that turned it on. The universe went from dark to light, and the math says it shouldn't have been able to. Let's combine the mystery of the missing dark matter with the mystery of the early black holes. What if they're the same thing? This is the hypothesis of primordial black holes. In the 1970s, Stephen Hawking suggested that in the chaotic high-pressure moments right after the Big Bang, long before any star formed, some pockets of space might have been so dense that they just collapsed instantly. These wouldn't be stellar black holes. They could be anything. They could be microscopic, the size of a proton, but with the mass of a mountain. Or they could be massive, thousands of times the sun's mass. If these things exist, they could solve a lot of problems at once. Why did we see giant black holes so early with James Webb? Because they were born that way in the Big Bang. They didn't need to grow. Where is the dark matter? Maybe it's not a particle. Maybe dark matter is just billions of these tiny ancient black holes floating everywhere, invisible but heavy. It's an elegant theory, but it's also terrifying. If dark matter is made of primordial black holes, it means the universe is a minefield. It means that right now, there could be an invisible black hole the size of an atom passing through our solar system. If a small one hit Earth, it would pass straight through like a bullet, causing a seismic shock. If a bigger one passed by, it could destabilize planetary orbits. We've looked for them. We've searched for the flashes of light they should make if they evaporate. We've watched stars to see if they twinkle as a black hole passes in front of them. We haven't found a smoking gun yet, but the LIGO Gravitational Wave Observatory has detected mergers of black holes that are unusually heavy, masses that fit the primordial profile better than the stellar one. So the question hangs there. Is the universe filled with ancient traps left over from creation? We've looked at impossible galaxies, ancient stars, and missing lithium. All of these problems point to one terrifying possibility. Our clock is broken. The standard age of the universe, 13.8 billion years, is the bedrock of modern cosmology. It's calculated based on the expansion rate, the Hubble constant, and the models of dark energy. But if you have stars older than the universe and galaxies that grew up too fast, maybe the number is just wrong. In July 2023, a physicist named Rajendra Gupta from the University of Ottawa published a paper that made headlines. He suggested that the universe might actually be 26.7 billion years old, nearly double the current estimate. How? By combining two radical ideas. One is tired light, an old theory from the 1920s that suggests light loses energy simply by traveling long distances, not just because space is expanding. The other is the idea that the physical constants of nature, like the speed of light or the strength of gravity, might evolve over time. If Gupta is right, the impossible galaxies found by James Webb suddenly make sense. They aren't impossible monsters. They just had twice as much time to grow. The Methuselah star isn't a paradox. It fits comfortably in the middle of the timeline, but fixing the age breaks almost everything else. It messes up the Big Bang nucleosynthesis, our cake recipe. It changes how we interpret the cosmic microwave background. Most astronomers don't buy it. Tired light has been debunked for decades because it blurs distant images which we don't see. But the fact that such a radical theory was published in a serious journal, Monthly Notices of the Royal Astronomical Society, shows how desperate the situation is. We're so backed into a corner by the data that we're willing to rewrite the age of the universe just to make the pieces fit. Let's leave the timeline and look at the neighbors, or rather the lack of them. If the universe is as old and as vast as we think it is, we shouldn't be alone. There are roughly 200 billion stars in our galaxy alone. Many have planets. Some are in the habitable zone. Even if life is incredibly rare, the sheer numbers dictate that we should see something, a signal, a structure, a probe. This is the heart of the Fermi Paradox. But when we point our radio telescopes at the sky, we hear nothing. The great silence. Now, silence might sound peaceful to you, but in astronomy, silence is terrifying. It's like walking into Times Square at noon on a Tuesday and finding it completely empty. No cars, no people, no noise, just wind. You wouldn't think everyone must be napping. You would think run. The silence suggests something is wrong with our assumptions about life. Is intelligence a suicidal trait? Do civilizations destroy themselves with nuclear fire, or AI the moment they get loud enough to be heard? Or is there a great filter, some inevitable catastrophe that wipes everyone out before they can spread to the stars? If the filter is behind us, like the origin of life, we're the lucky lottery winners. But if the filter is ahead of us, then the silence isn't empty. It's a graveyard. and we're just the next grave waiting to be dug. Every day we survive without finding aliens actually increases the probability that the filter is still waiting for us. Finding a simple bacteria on Mars would be good news. Finding ruins of an ancient city on Mars would be the worst news in human history, because it would mean they got this far and died. And we're next. While we argue about invisible civilizations and dark forests, in October 2017, something actually showed up on our doorstep. The Pan-STARRS telescope in Hawaii spotted a faint, fast-moving object tumbling through our solar system. At first, we thought it was a comet, then an asteroid, but as we tracked its orbit, we realized it wasn't from here. It had come from interstellar space, diving into our system from the direction of Vega, swinging past the sun at nearly 200,000 miles per hour and shooting back out into the dark. We named it Oumuamua, Hawaiian for scout, or first messenger from afar. And the more we looked at the data, the weirder it got. First, the shape. The light curve suggested it was incredibly elongated, like a cigar or a pancake, at least 10 times longer than it was wide. We've never seen a natural space rock with those dimensions. Asteroids are usually potato-shaped chunks. This looked engineered. But the real smoking gun was its movement. As Oumuamua left the solar system, it accelerated. Now, comets do this. When a comet gets close to the sun, the ice on its surface warms up and shoots out jets of gas, acting like tiny thrusters. This outgassing gives comets a little non-gravitational push. But here's the problem. Oumuamua had no tail, no gas, no dust coma. The Spitzer Space Telescope looked for heat from any outgassing and saw absolutely nothing. So, you have a heavy cigar-shaped object accelerating without any visible propulsion. This led Avi Loeb, the chair of Harvard's astronomy department, to propose a controversial hypothesis. What if it was a light sail, a piece of defunct alien technology pushed by the pressure of sunlight? The mainstream scientific community pushed back hard. They proposed complex theories. Maybe it was a hydrogen iceberg that evaporated invisibly, though hydrogen ice is incredibly hard to form. Or a nitrogen fragment from an exploded Pluto-like planet. Or a dust bunny made of ultralight fractals. But every natural explanation has a hole in it. Hydrogen ice would have evaporated long before it reached us. Nitrogen fragments are statistically rare. The light sail theory, while radical, actually fits the data of the acceleration perfectly. Whether it was a rock or a wreck, Oumuamua proved one thing. We're not isolated. Stuff from out there is coming in here. And if one object passed through, how many millions did we miss because we weren't looking? It was a wake-up call. The doorbell rang, and by the time we got to the door, the visitor was already walking away down the street. Let's step back from the objects and look at the rules of the game itself. This is the mystery that bothers physicists more than any black hole or alien signal. It's the mystery of fine-tuning. If you look at the fundamental constants of nature, the numbers that define our reality, they seem suspiciously perfect for life. Take the strong nuclear force which holds atomic nuclei together. If it were just 2% stronger, hydrogen would fuse into helium instantly after the Big Bang. There would be no hydrogen left to make water, no long-burning stars like our sun. The universe would have burned out in a flash. If it were 2% weaker, protons and neutrons wouldn't stick together at all. No atoms, just a soup of particles. Take the cosmological constant dark energy. Its value is incredibly small. 0 point followed by 120 zeros, and then a 1. If it was slightly larger, the universe would have ripped itself apart before galaxies could form. If it were slightly smaller, the universe would have collapsed back into a crunch within seconds. It's like walking into a room and finding a pencil balanced perfectly on its tip. It's theoretically possible, but statistically it shouldn't happen. We call this the anthropic principle. The idea is that we observe these values because if they were different, we wouldn't be here to observe them. It's a selection bias, but that feels unsatisfying. It feels like saying I won the lottery, because if I didn't win, I wouldn't be holding the check. It doesn't explain why we won. This leads to two conclusions, both of which are mind-bending. One, there's a multiverse. There are infinite universes with random constants. Most are dead, empty wastelands. We just happen to live in one of the few habitable bubbles, because obviously we can't live in the dead ones. 2. The universe was designed. Simulation theory or some underlying creative principle set the dials exactly where they needed to be. Science hates the design answer because it sounds like religion. But the multiverse answer requires an infinite number of unobservable universes. Just to explain this one, it's a choice between an infinite lottery or a rigged game. And right now, we can't tell which one we're playing. Now we enter the territory where the actual machinery of physics starts to grind gears. If you thought the mysteries so far were just things we haven't found yet, get ready for things that prove we're wrong. The biggest crisis in modern cosmology is called the Hubble tension. It's a simple question. How fast is the universe expanding? We have two main ways to measure the speed known as the Hubble constant. Method 1, the early universe. We look at the cosmic microwave background with the Planck satellite. We measure the physics of the infant universe, put those numbers into our best model, lambda CDM, and fast forward 13 billion years to predict how fast we should be expanding today. The answer comes out to 67 kilometers per second per megaparsec. It's a precise clean number derived from fundamental physics. Method 2, the late universe. We look at the actual stars around us. We use standard candles, pulsing Cepheid stars, and exploding Type Ia supernovae to measure distances directly. It's like using a tape measure. We see how fast galaxies are moving away from us right now. The answer comes out to 73 or 74 kilometers per second per megaparsec. 67 versus 74. Those numbers don't match, and the error bars don't overlap. This is a 5 sigma discrepancy, which in physics means this is not a fluke. The chance of this being a statistical accident is 1 in 3.5 million. It's like measuring your height. You measure it with a ruler and get 6 feet. Your doctor calculates it based on your bone density and gets 5'8". Both measurements seem perfect. Both methods are sound, but you can't be both heights at once. Someone is wrong. For years, astronomers thought it was the instruments. Maybe Planck had a glitch. No. Other CMB experiments confirmed it. Maybe the Cepheids are dusty. No. Hubble and now James Webb have remeasured them with insane precision, and the tension is still there. In fact, it's getting worse. This implies something terrifying. Our model of the universe is missing a gear. The prediction from the early universe fails to match the reality of the late universe. This means something happened in between that we don't understand. Did dark energy change over time? Is there a new type of neutrino? Or does gravity behave differently on cosmic scales? The Hubble tension isn't just a debate about numbers. It's a sign that the standard model, our masterpiece, is broken. Let's dig deeper into why the Hubble tension is so stubborn. Maybe the tape measure is broken. This is what the early universe team argues. They say, look, Cepheid variables are tricky. They live in crowded star clusters. Maybe you're blending their light with other stars. To fix this, astronomers developed a completely different tape measure, the tip of the red giant branch. Red giant stars reach a very specific peak brightness before they ignite helium in their cores. It's a standard physical limit, like a light bulb that pops at exactly 100 watts because it's based on clear nuclear physics. It should be cleaner than Cepheids. So Wendy Friedman and her team used TRGB to measure the expansion. Everyone held their breath. If TRGB gave 67, the early universe team wins. If it gave 74, the late universe team wins. The answer came back 69.8. It landed right in the middle. It didn't solve the tension. It complicated it. Now we have 3 numbers. The early universe says 67. The supernovae say 74. The red giants say 70. This is a mess. It suggests that every method has systematic errors we don't understand, or that the universe is even more complex than a simple speeding up curve. Then, James Webb stepped in to settle the Cepheid argument. In late 2023, it looked at the same stars Hubble used, but with sharper vision to separate them from the crowd. The hope was that the 74 number would drop down to 67 once the noise was cleared. It didn't happen. The Webb data confirmed the Hubble data. The number stayed high. The tension is real. The tape measure is accurate, which means the prediction is wrong. The universe is expanding faster than physics says it should. It's running away from our mathematics. And we don't know what's pushing the accelerator. So, If the measurements are right, how do we fix the model? The leading contender is a desperate idea called early dark energy. We usually think of dark energy as the force that's pushing the universe apart today. It turned on about 5 billion years ago. Before that, gravity was winning. But to bridge the gap between 67 and 74, some physicists suggest that maybe there was a second burst of dark energy right at the beginning. A brief flash of anti-gravity that happened just before the cosmic microwave background was released. Imagine the universe expanding. Suddenly, a new field turns on, kicks the expansion into overdrive for a few 100,000 years, and then vanishes without a trace. This extra kick would change the size of the sound horizon in the early universe, which would change our calibration for the CMB. If you plug this early dark energy into the equations, the predicted value of 67 jumps up to about 72. It fits. It solves the tension. But it feels like a cheat. It feels like adding a fudge factor. Why would a mysterious energy field turn on, push the universe, and then turn off exactly when we needed it to? There's no evidence for this field in particle physics. It's a mathematical patch like using duct tape to fix a cracking dam. And even with early dark energy, other problems pop up. It makes the S8 tension, another crisis about how clumpy matter is, even worse. It's a game of whack-a-mole. You fix the expansion rate, and you break the structure of galaxies. You fix the galaxies, and you break the age of the universe. This tells us that we aren't just missing a variable. We're missing a fundamental concept. The machine of the universe has parts we haven't identified. And right now, smoke is coming out of the engine. If the expansion of the universe is confusing, let's look at something that should be rock solid. The constants of nature. Take a number called alpha, the fine structure constant. It's roughly 1 over 137. This number controls the strength of the electromagnetic force. It dictates how electrons cling to atoms, how light interacts with matter, and ultimately how chemistry works. It's one of the pillars of reality. If alpha were slightly different, stars wouldn't burn the same way, and carbon-based life might be impossible. Standard physics assumes that alpha is the same everywhere, on Earth, on Mars, in the Andromeda galaxy, and at the edge of the visible universe. It's a constant, right? Well, maybe not. In the late 90s, a team led by John Webb from the University of New South Wales started analyzing the light from distant quasars. As this light travels billions of years to reach us, it passes through gas clouds. The atoms in those clouds absorb specific wavelengths, creating a barcode of dark lines in the spectrum. The spacing of those lines depends entirely on alpha. By measuring the spacing, you can measure the strength of electromagnetism billions of years ago. John Webb's team found something impossible. The alpha in one direction of the sky was slightly smaller than on Earth. In the opposite direction, it was slightly larger. It looked like a dipole, a gradient across the entire universe. The difference was tiny, just a few parts per million, but statistically significant. It suggested that the laws of physics aren't universal. They're local, like how the temperature changes depending on where you are in a room. Maybe the strength of electromagnetism changes depending on where you are in the cosmos. If this is true, it's devastating for the Standard Model. It destroys the equivalence principle, the heart of Einstein's relativity. It means there's a preferred direction in the universe. Hello again, axis of evil. Critics have attacked the data for 20 years, blaming telescope calibration. But newer studies using entirely different telescopes have found hints of the same pattern. If alpha isn't constant, then constant is just a word we use to comfort ourselves. Reality might be fluid. While we question constants, let's revisit our old friend dark matter. We treat it as an essential ingredient. You can't build a galaxy without dark matter. That's the rule. The visible stars don't have enough gravity to hold themselves together. They would fly apart without the invisible glue of dark matter. But in 2018, astronomers found a galaxy that forgot the glue. It's called NGC 1052 DF2, or just DF2. It's an ultra-diffuse galaxy looking like a ghostly smudge of stars. When astronomers measured how fast the star clusters inside it were moving, they were shocked. The stars were moving slowly, lazily. Their speed matched the gravity of the visible stars exactly. There was no room for dark matter in the equation. If there was any hidden mass, the stars would be zipping around much faster. The calculated ratio of dark matter to normal matter was basically 0. This broke everyone's brain for two opposing reasons. Reason 1, it challenges galaxy formation. How do you gather gas and stars into a clump without a dark matter well to pull them in? It's like building a house without a frame. Reason 2, ironically, it killed the alternative theories to dark matter. Theories like MOND, modified Newtonian dynamics, argue that dark matter doesn't exist. Gravity just works differently at large scales. But if gravity works differently, it should work differently everywhere. Every diffuse galaxy should show the MOND effect. The fact that DF2 doesn't show it implies that dark matter is a physical substance, stuff that can be separated from a galaxy, rather than a universal law of gravity. So DF2 proved dark matter is real by not having any. But it also proved that our models of how galaxies form are incomplete because we have no idea how to make a galaxy that's naked. And then we found another one, DF4. So there's a whole population of ghost galaxies out there defying the rules of construction. Let's go deeper. Let's talk about why you exist at all. According to the standard model of particle physics, matter and antimatter are created in equal pairs. Symmetry. If you turn energy into mass, E equals mc squared, you get one electron and one positron, one proton and one antiproton. They're mirror images. And when they meet, they annihilate. They turn back into pure energy. Poof. So in the Big Bang, which was a massive explosion of energy, the universe should have created 50% matter and 50% antimatter. As the universe cooled, these pairs should have collided, annihilated each other, and left behind nothing. Just a bath of photons, light, but no stuff. But look around. There's stuff. There are stars. There's a screen in front of you. There's you. We live in a universe made almost entirely of matter. Antimatter is incredibly rare. We can make tiny amounts in particle accelerators, but we don't see anti-galaxies or anti-stars. Where did the antimatter go? This is the baryon asymmetry problem. Somehow, in the first fraction of a second, the universe favored matter. For every billion pairs of antimatter created, 1,000,001 particles of matter were created. The billion pairs killed each other, leaving that one lonely survivor. We're the survivors. We're the error in the math. Physicists call this CP violation, a breach in the symmetry of charge and parity. We've seen tiny examples of it in particles called kaons and B-mesons. But the effect is way too small to explain the universe we see. It's like trying to empty an ocean with a teaspoon. The math says we shouldn't be here. The fact that we are means there's a massive mechanism in the early universe, maybe related to neutrinos or the Higgs field that we haven't discovered yet. We're the leftovers of a cosmic massacre, and we don't know why we were spared. If the universe is hiding particles from us, we might be on the verge of finding them, not with a telescope, but with a magnet. Meet the muon. It's basically a heavy electron. It's unstable, short-lived, and acts like a tiny magnet. If you put a muon in a magnetic field, it wobbles, precesses like a spinning top. The standard model can predict exactly how fast it should wobble. This prediction, called G-factor, is incredibly precise. It accounts for every known particle in the universe: photons, quarks, Higgs bosons popping in and out of the vacuum and nudging the muon. It's a calculation involving thousands of diagrams and supercomputers. In 2021, the Fermilab Muon G2 experiment released its latest results. They shot billions of muons around a giant magnetic ring to measure the wobble. The result? The muon is wobbling too fast. The difference is tiny, 0.00 something, but it has reached a statistical confidence of 4.2 sigma. That's tantalizingly close to the 5 sigma gold standard for discovery. Why is it wobbling too fast? Because something is pushing it, something that isn't in the standard model. It could be a Z-prime boson, it could be a leptoquark, it could be a supersymmetric partner particle, or it could be dark matter interacting with the muon. Whatever it is, it's a ghost in the machine. The muon is feeling a force we don't know about. This tiny wobble is currently the strongest evidence we have that the standard model is incomplete. The bedrock of particle physics has a crack in it, and the muon is dancing right over the edge. And finally, we arrive at the single biggest embarrassment in the history of theoretical physics, the vacuum catastrophe. We tend to think of a vacuum as empty, nothing. But quantum mechanics says that's wrong. The vacuum is alive. It's seething with virtual particles popping in and out of existence, fluctuations in the quantum fields. Since energy and mass are equivalent, this seething activity has energy. Gravity should feel this energy. It should pull on the fabric of space-time. So physicists decided to calculate how much energy is in the vacuum of space. They took quantum field theory, summed up the contributions from all the fields, and got a number, a huge number. Then they looked at the actual universe. We can measure the energy of the vacuum by looking at how fast the universe is accelerating. Dark energy. The theoretical number is larger than the observed number by a factor of 10 to the power of 120. That's a 1 with 120 zeros after it. It's not just wrong, it's spectacularly hilariously wrong. It's the worst prediction in science. If the theoretical number were true, the universe would have expanded so fast that no atoms could have ever formed or collapsed instantly. The fact that space is relatively calm means that something is canceling out almost all of that quantum energy perfectly to 120 decimal places, but leaving just a tiny bit left over to drive the current expansion. We have no idea how this cancellation happens. Is it a coincidence? Is it a symmetry we haven't found? Or do we fundamentally misunderstand what a vacuum is? This discrepancy suggests that our two best theories, quantum mechanics for the very small and general relativity for the very big, are violently incompatible when they try to talk about nothing. The vacuum catastrophe is a theoretical embarrassment, but we can actually see this strange energy in the lab. It's called the Casimir effect, and it's the closest thing physics has to magic. In 1948, Dutch physicist Hendrik Casimir predicted that if you took two uncharged metal plates and placed them incredibly close together in a perfect vacuum, they would move, not because of gravity, not because of magnetism, but because of the nothingness between them. Here's the logic. The vacuum is full of virtual particles behaving like waves. Outside the plates, waves of all sizes can exist. But between the plates, the space is so tight that only small waves fit. It's like trying to play a low bass note on a tiny guitar string. It just doesn't work. Because there are fewer waves pushing from the inside than from the outside, there's a pressure difference. The empty space outside pushes harder than the empty space inside. The result? The plates are crushed together by the vacuum itself. This force is tiny but real. In 1997, Steve Lamoureux at Los Alamos National Laboratory measured it precisely. He brought a sphere and a plate to within a few micrometers of each other and detected a force of about 1/1000th of a Newton. That matches the theory perfectly. This proves that empty space has mechanical strength. It has weight. It can push things around. So, if the vacuum can crush metal plates in a lab, why isn't it crushing the universe or ripping it apart? The fact that we can measure this energy on a small scale makes the vacuum catastrophe on the large scale even more baffling. We know the energy is there. We can touch it. But when we look at the stars, it's missing in action. If empty space is unstable, what about matter itself? We assume that atoms are forever. A proton is. A proton is a proton. It was born in the Big Bang, and it will survive until the end of time. But most grand unified theories, the theories that try to combine all the forces of nature into one, say that's wrong. They predict that protons are mortal. Eventually, every proton in the universe should break down into a positron and a pion. If this is true, then all matter is slowly evaporating. You, the Earth, the Sun, we're all made of temporary ingredients. To test this, scientists built a massive detector called Super Kamiokande. It's a tank filled with 50,000 tons of ultra-pure water, buried 1,000 meters underground in a Japanese mine to shield it from cosmic rays. The tank is lined with 11,000 light sensors. The idea is simple. If a single proton in all that water decays, it will emit a tiny flash of light. They've been watching for decades, and they've seen nothing. The proton seems to be stable for at least 10 to the power of 34 years. That's a 1 followed by 34 zeros. That's billions of times longer than the age of the universe. This sounds like good news. We aren't going to dissolve anytime soon. But for physicists, it's a disaster. It means the grand unified theories that predict proton decay are wrong. We tried to unify the forces, and the proton said no. It suggests that there's a fundamental wall between the forces of nature that we can't break down. Or perhaps the decay takes so long that we just haven't been lucky enough to catch one yet. Either way, the stability of the proton is a silence that screams that our best theories are missing something huge. And this leads us to the ultimate wall, the one we've been banging our heads against for a century, the incompatibility of quantum mechanics and general relativity. We have two rulebooks for the universe. Rulebook 1, General Relativity. It says space is smooth like a trampoline. Gravity is just the curvature of that fabric. It works perfectly for stars, galaxies, and black holes. Rulebook 2, Quantum Mechanics. It says the world is pixelated, made of discrete chunks of energy. It works perfectly for atoms and subatomic particles. Both rulebooks are verified by thousands of experiments, but they speak different languages. If you try to combine them, if you try to calculate the gravity of a single electron, the math explodes. You get infinity as an answer. Infinity is not a number. It's the equations telling you that they're broken. This crisis happens at the center of a black hole, a singularity. It's a point where a massive amount of stuff, relativity, is crushed into a tiny space, quantum. The two theories fight and physics collapses. We simply do not know what happens there. The laws of nature stop working. We've tried to fix this with string theory, which says particles are vibrating loops. We've tried loop quantum gravity, which says space is made of tiny woven knots. But neither theory has produced a single testable prediction. We're stuck. We're using two different maps for the same territory, and the borders don't line up. Until we find a theory of quantum gravity, we don't really understand the universe. We only understand the easy parts. The core, the singularity, remains completely hidden from us. Now we enter the final chapter, the one where we question not just the objects in the universe, but the stage itself. Let's start with time. You feel time flowing. The past is gone. The future hasn't happened. The present is the only thing that's real. That's how it feels to be human. But Einstein's relativity says that feeling is a lie. In relativity, time is just another dimension like length, width, or height. It's part of a four-dimensional structure called spacetime. And just like all of space exists at once, all of time exists at once. This is called the block universe. Imagine a loaf of bread. Every slice is a moment in time. The dinosaurs are on one slice, you're on another. The death of the sun is on another. Just because you're currently conscious on your slice doesn't mean the other slices aren't there. They're all equally real. This means the past isn't gone. It's just down the road. And the future isn't unwritten. It's already there waiting for you to experience it. This destroys the idea of free will. If the future already exists in the four-dimensional block, you're just riding a roller coaster track that's already been built. You can't change the turn that's coming up. Physicists argue about this constantly. Some say quantum mechanics reintroduces randomness and breaks the block. Others say the math of relativity is clear. Simultaneity is relative, so there's no universal now, and therefore, the past and future must exist. If they're right, then the flow of time is just a trick of our biology, a hallucination to stop everything from happening at once. If you think the block universe is bad, let me introduce you to the Boltzmann brain. This is a paradox that comes from the laws of thermodynamics and entropy. Ludwig Boltzmann, a 19th century physicist, suggested that the universe could be a random fluctuation. Out of an eternal chaotic void, particles just happen to come together to form stars and galaxies. But here's the problem with probability. It's much, much easier to form a small, simple thing by chance than a huge, complex thing. It's exponentially more likely for random particles to come together and form just a human brain, complete with false memories of a past life, than it is to form an entire universe with billions of galaxies and real history. According to the math, for every one real universe, there should be trillions of lone brains floating in the void, hallucinating that they're reading a script about space mysteries. So statistically speaking, you're probably not a person sitting in a room. You're probably a Boltzmann brain floating in deep space, imagining the room, imagining the screen, and imagining me telling you this. This is not a joke. It's a serious problem in cosmology. If our theories predict that freak observers are more common than real observers, then our theories are wrong. We call this the measure problem. We have to find a reason why the universe favors big, complex structures over simple, lonely brains. But so far, the math suggests that reality is the less likely option. It's a thought that makes you want to check if the walls of your room are solid. But of course, in a hallucination, they would feel solid, wouldn't they? If the idea that you're a floating brain is too abstract, let's look for something harder like pixels. If we're living in a simulation, a matrix-style digital reality created by a post-human civilization, there should be limitations. Every computer has a limit to its processing power. It has a resolution. It has to cut corners to save memory. So physicists have started looking for the pixels of our universe, and disturbingly, they might have found them. One clue comes from high-energy cosmic rays. These are particles traveling across the universe at nearly the speed of light. In 1966, 3 physicists, Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin, calculated a theoretical speed limit for these particles, called the GZK limit. They argued that if a cosmic ray travels too fast, above 5 × 10 to the 19th electron volts, it should crash into the photons of the cosmic microwave background and lose energy. It's like trying to run through a crowd. Eventually, you bump into someone and slow down. This acts like a hard cap on velocity in the universe code. It looks suspiciously like a variable constraint in a software program to prevent stack overflow. Another clue is the Planck length. This is the smallest possible unit of measurement, about 1.6 × 10 to the -35 meters. You cannot measure anything smaller. It's the absolute bottom. Why does the universe have a minimum resolution? Why isn't space infinitely smooth? Simulation theorists argue that the Planck length is the grid size of the simulation. It's the pixel. Then there's error-correcting code. In theoretical physics, specifically in string theory and supersymmetry, James Gates discovered mathematical structures that look identical to binary error-correcting codes used in modern web browsers, specifically Adinkra codes. It's literally computer code embedded in the equations that describe the fabric of reality. Is this proof? No. It could be that math is just the language of nature, and computers use math, so they look similar. But the fact that the universe has hard limits on speed, resolution, and information density makes it look a lot less like a wild organic place, and a lot more like a rendered environment running on a very, very powerful machine. And, if that's true, the scariest question isn't how does it work? It's who's holding the off switch? Speaking of off switches, physics has identified a way the universe could end today without warning. It's called false vacuum decay, and it has to do with the Higgs boson. The Higgs field is what gives particles mass. Think of it as a surface. Everything in the universe wants to be at the lowest possible energy state, the bottom of the valley. We assume that our vacuum, the state of empty space, is at the true bottom, the true vacuum, stable, safe. But measurements of the mass of the top quark and the Higgs boson suggest that we might be wrong. We might be in a false vacuum. Imagine standing on a ledge halfway down a cliff, thinking you're at the bottom. You're stable for now, but the real bottom is 1,000 feet further down. All it would take is a tiny push to send you falling. In quantum mechanics, this push can happen spontaneously through a process called quantum tunneling. At any moment in any random spot in the universe, a tiny bubble of true vacuum could appear. Inside this bubble, the laws of physics would be rewritten. The constants of nature would change. Chemistry would become impossible. Atoms would fall apart. And here's the bad news. This bubble would expand at the speed of light. Because it moves at light speed, you would never see it coming. There would be no warning, no flash on the horizon. 1 second, you're there. The next nanosecond, your atoms have dissociated, and the fundamental structure of your reality has been deleted. This bubble would eat the entire universe, converting our false vacuum into true vacuum. It's the ultimate cosmic format. Some calculations suggest the universe is metastable, meaning we're safe for billions of years. But others suggest the edge is closer than we think. We're living on a tightrope, and we don't even know how far down the drop is. It's the ultimate reminder that our existence is fragile, dependent on energy fields staying balanced on a knife's edge. If the vacuum doesn't delete us, dark energy might tear us apart. We know the universe is expanding. We know the expansion is accelerating. For a long time, we thought this just meant galaxies would drift away from each other until the sky was dark. A lonely, cold death called the Big Freeze. But recent data suggests a much more violent ending, the Big Rip. This depends on a number called W, the equation of state parameter for dark energy. It measures how the density of dark energy changes as the universe expands. If W is exactly -1, the density stays constant, standard model. But if W, is less than -1, say -1.1, then dark energy gets stronger over time. This is called phantom energy. If phantom energy is real, the expansion will go rogue. It won't just push galaxies apart, it will overcome gravity entirely. It will rip galaxies apart. Then it will rip solar systems apart. Planets will be flung from their stars. In the final moments, the expansion force will become stronger than the electromagnetic force holding atoms together. Stars and planets will explode. Then molecules will be shredded. Finally, in the last fraction of a second, atoms themselves will be ripped apart. Even the fabric of spacetime will be torn asunder. The universe ends not with a whimper, but with a violent shredding of everything that exists. Current measurements from the Planck satellite put W at about -1.03 with error bars. That puts us dangerously close to the phantom energy zone. We can't rule it out. So, while we worry about asteroids or climate change, the universe itself might have an expiration date where the physics holding your body together simply stops working. So, is the end really the end? Sir Roger Penrose, a Nobel Prize winner and one of the smartest minds in physics, says no. He believes in conformal cyclic cosmology. The idea is that the Big Bang wasn't the beginning. It was just a transition, a bounce. Penrose argues that in the very distant future, after all the stars have burned out and black holes have evaporated via Hawking radiation, the universe will contain nothing but photons, light. Here's the trick. Photons have no mass. And because they have no mass, they don't experience time or scale. To a photon, a universe that's infinitely big looks exactly the same as a universe that's infinitely small. The concept of size vanishes at this moment. Penrose says the geometry of the universe resets. The infinite cold future of one aeon becomes the hot, dense Big Bang of the next aeon. It's a beautiful, poetic cycle. But Penrose claims there's evidence. He points to Hawking points, strange rings in the cosmic microwave background. He argues that these rings are the gravitational echoes of supermassive black hole collisions from the previous universe, ghostly ripples that survived the end of the world to leave a fingerprint on our sky. Most cosmologists are skeptical. They say the rings are statistical noise. But if Penrose is right, then we're living on a graveyard. The atoms in your body might be recycled from the ashes of 1 trillion previous universes. It changes the story from Genesis to reincarnation. We're just one breath in an eternal lung expanding and contracting forever. It makes our mysteries seem small, but it also makes our existence infinitely recurring. We've reached the edge of physics. We've talked about simulations, tears in reality, and eternal cycles. But there might be a final logical wall that stops us from ever knowing the truth. In 1931, mathematician Kurt Gödel dropped a bomb on the world of logic. He proved his incompleteness theorems. In simple terms, he proved that in any complex logical system like mathematics, there will always be statements that are true, but cannot be proven within the system. You cannot use math to prove all of math. There will always be blind spots. Why does this matter for space? Because physics is built on math. If the universe is a mathematical system, then Gödel's theorem applies to it too. This implies that a theory of everything, a single equation that explains all of reality, might be impossible. Not because we aren't smart enough, but because logic itself forbids it. There might be laws of physics that are true, but we can never prove them. There might be constants that have values for no reason we can verify. We might be trapped inside a system that's fundamentally incapable of explaining itself. This is the ultimate humility. We're trying to decode the universe using a language, math, that has built-in limits. It's like trying to draw a perfect circle using pixels. You can get close, but you'll never get it perfect. The mysteries we've listed, the cold spot, the Hubble tension, the vacuum energy might not be puzzles waiting to be solved. They might be the Gödelian cracks in the system, the places where logic fails. And if that's true, then the feeling that nothing makes sense anymore isn't confusion. It's the correct answer. So where does that leave us? We started this journey looking for errors in the map. We found cold spots that shouldn't exist, and galaxies flowing like rivers toward unseen monsters. We looked at the timeline and found stars older than the universe, and black holes that grew too fast. We looked for neighbors and found only a terrifying weaponized silence. We drilled down into the foundation of physics and found cracks in the constants, particles behaving badly, and a vacuum energy calculation that's wrong by 120 orders of magnitude. It's tempting to look at this list of 50+ anomalies and say, well, science is broken. It's tempting to throw up our hands and say, we know nothing. But that's the wrong takeaway. The fact that we found these anomalies is the victory. 100 years ago, we didn't know enough to be confused. We thought the Milky Way was the entire universe. We thought time was constant. We thought atoms were solid balls. The confusion we feel now is a symptom of higher resolution. We're seeing the glitches because we're finally looking closely enough. However, the sheer number of these problems suggests that we're approaching a paradigm shift. Thomas Kuhn coined this term. Science doesn't move in a straight line. It stays steady for a while, accumulating anomalies that don't fit until the pressure becomes too great. Then suddenly, the old model shatters, and a new one takes its place. Newtonian gravity worked perfectly until Mercury's orbit didn't fit. Then, Einstein shattered it. We're in that Mercury moment right now. The Standard Model is creaking under the weight of the Hubble tension, the JWST galaxies, and the dark sector. Something is about to break. And when it does, our view of reality will change as drastically as it did when we realized the Earth wasn't flat. But there's a deeper twist, a scarier one. Throughout this entire exploration, we've assumed that making sense is the default state of the universe. We assume that logic, cause and effect, and math are the bedrock of reality. We assume the universe should be understandable to a primate brain that evolved to hunt antelopes on the savannah. Why? Why should the cosmos care if we understand it? The anomalies might not be errors. They might be windows into the true nature of things, a nature that's chaotic, non-local, and fundamentally alien to human logic. The quantum world already hints at this. Things can be in two places at once. Cats can be alive and dead. The weirdness isn't a bug, it's a feature. Maybe the reason we can't explain the cold spot or the axis of evil is that we're trying to force a non-linear multi-dimensional universe into a three-dimensional linear story. We're trying to read a novel written in a language that has no alphabet. The glitches are just the moments where our translation software fails. And if that's true, then the mystery is the point. The fear we feel when we look at the great void or the false vacuum isn't just fear of the unknown. It's the vertigo of realizing that we're small and the universe is vast, and it's under no obligation to follow our rules. We live on a small rock orbiting a mediocre star in the suburbs of a standard spiral galaxy. We've built a little island of light called science to keep the dark away. And it works. It keeps the lights on and the planes flying. But every time we point a telescope into the dark, we're reminded that our island is tiny and the ocean is infinite. We've seen that the history of the universe is darker and stranger than we imagined. We've seen that our safety is an illusion maintained by fragile energy fields. We've seen that we're likely alone or worse, hiding in a forest full of predators. The next time you look up at the night sky, don't just see the pretty lights. Look at the black space between them. That's where the dark matter is flowing. That's where the vacuum energy is seething. That's where the signals from dead civilizations might be passing through you right now. We're drifting in the dark. We don't have a map. The clock is broken. The compass is spinning. And the only thing we know for sure is that nothing makes sense anymore. And honestly, I wouldn't have it any other way. Because a universe that makes sense is a small universe. A universe that terrifies us, that's a universe worth exploring.